Whether you're a pro football player or don't really know much about the sport, most people can agree on the fact that American football fields are huge. At an area of over 5,000 meters squared, that's equal to about 10,000 of these markers with the cap on. But what if you could somehow fit a material that has 1.5 times this area into just 1 teaspoon and have it weigh only a gram? Sounds crazy, right? Well, what is this material, and how is this even possible? This material is called a metal organic framework, or MOF, and it is a highly porous crystalline structure made up of metal ions, which are inorganic, or clusters, and a linker, which is organic. And they are connected to form a cage-like structure with tons of open space inside. Taking a step back, this ball has a lower area than this one, as the pores add to the area. Similarly, MOFs are able to have such a high surface area due to their countless pores. In fact, a variety developed at Northwestern has the highest surface area material. With all their unique properties, there is truly nothing else like them, and they outperform every previously known class of material in terms of flexibility. So, why are they important? Their high surface area and plenty of pores make them very effective to tackle some of the largest issues in the world today. They can help fight pollution as gas sensors, as varieties can detect and capture harmful gases in the air, making them small, inexpensive, and energy-efficient gas sensors. One of these gases is carbon dioxide. The MOF pictured here capture the carbon between the manganese and amine groups. This chain effectively stores the carbon dioxide in a linear pattern, which is very similar to the way plant enzyme RUBISCO stores its carbon. Coating them off with an electrode forms an electronic sensor that can detect sulfur dioxide gas, or using aluminum as the metal, as used in MFM 300, aluminum filters NO2 and stores ammonia. The list goes on of the possibilities. When MOF filtration techniques were tested with water in Flint, Michigan, the test showed that MOF can, in a matter of seconds, reduce lead concentrations to 2 parts per billion, a level that the U.S. EPA and World Health Organization deemed drinkable. MOF vaccines are also used in biocompatible polymer frameworks that can freeze the proteins inside the vaccines. These can then dissolve when injected into human skin. Particularly, this helps areas that are very remote and don't have reliable power, because it can help healthcare providers transport and administer them. They can also be used in micro and nano robotics for drug delivery systems. The MOF's pores can be filled with the drug and used in a MOFbot, which is a type of microbot for controlled motion and delivery. These are propelled by flagella in bacteria, which can swim through and follow trajectories in 3 dimensions to control the weak rotational magnetic fields. So, while these are just discovered in the last decade, they have plenty of potential that can be used to combat issues in the world today. These discoveries are just a start, and there are plenty more to be made. I'm excited to see what's to come.